Okay, 6.3.1, which is the converse of the Pythagorean theorem. And I've stated it here. I'm going to not really prove it because the proof is a little bit trivial. If the square of the longest side of a triangle is equal to the sum of the squares of the other two, then the triangle is right. And the measure opposite the longest side is 90 degrees. What I've done here is show a few length triples, so things that are very close to what right triangles are, and I'm going to try to show you that there are triangles that are made up. So in this problem, this screencast, we're going to talk a little bit about these things called Pythagorean triples, and I've got a couple of them here, 3, 4, and 5s. And if you see what I'm going to try to do here is create, so 5, again, the longest side is the only candidate for to be the hypotenuse. And then I'm just going to pull this in, and these lengths are preset to be 3, 4, and 5, so they're not going to change any length. So you can see what happens here. It's not perfect, but this is about trying to get the lengths to be just about right for the triangles. All right, so there's a 3, 4, 5. I can swing that in. Okay, there are also these 5, 12, 13s. And again, you can check what's going on here. Let's see if I can bring this down and be a little smarter. So this comes up a little bit. Goes off the screen, so I can't really see it. So here's a 5, 12, 13. Bring that down a tiny bit, and there we go. And of course, it should be obvious, but maybe not. The right angles are here and here, in the 5, 12, 13s and the 3, 4, 5s. I want to make it very clear, of course, that just because the numbers don't have to happen to be integers, as in 3, 4, 5, 5, 12, 13, there are plenty of these. So this is a 2 and a 3. Let's see if I can do this. And then this is, what does this have to be? This is the square root of, let's see, 3 squared plus 2 squared is 13. So this little number, and again, it won't let me do anything squares, this is the square root of 13. And again, just to finish off, there are collections of things called Pythagorean triples. So when the numbers are nice integers, there's a family of all of these. So there's a 3, 4, 5 family. Let's see if I can change this up. 3, 4, 5 family. There's a 5, 12, 13 family. There's an 8, 15, 17 triple, and a 7, 24, 25 set of triangles. Okay, and it turns out, if this is an area of study that you're interested in, this is an infinite number. There are an infinite number of these kinds of triples, and it's a huge area of study if you want to. Okay, that's 6.3.1.